Okay, what we're going to do to solve this problem, define the vector x such that ax minus b is minimized, where a is, of course, the transformation that's defined by this system of equations, and b is a set of y values, vector it's a set of y values, and x is a vector a, b, c in R3. We can picture this situation in terms of a transformation. T of v equals a times v. T takes the space v, which is an R3 space, and w, which is an R5 space. It maps every vector in v to some vector in w. Now, the image of the entire R3 space can't have dimension bigger than 3. Remember that the row space over here can't have dimension bigger than 3. And the column space over here has to have the same dimension as the row space. Also, the column space is the row space of A transpose, as we've discussed. We don't need to know that just yet, but we kind of want to keep that in mind. We'll have to use it. Okay. Since, by the nature of the real world data we have here, since we don't have the same value of t for any 2 points, we expect that the rank of this transformation, that is, the dimension of the row space, will be 3, so that all of R3 will be the row space. So, we expect in this case, this is not always the case, that the row space of A is all of V. Okay, the space V, which is the R3 space. So we expect that the column space also has dimension 3, and that the dimension, the row space of the transpose matrix will still have dimension 3. As it must, if this row space has dimension 3. Okay. Now I've depicted over here the column space just by an axis, just by a one-dimensional space. And I've depicted the null space of A transpose by a one-dimensional space. We know that any matrix breaks the space, I'm not going to be real specific about this, breaks the space into a row space and a column space that are mutually orthogonal and that have dimension that adds up to the dimension of the space. So we conclude that the row space having dimension 3, row space of A transpose having dimension 3, the column space of A being equal to the row space of A transpose, having dimension 3, the null space of A transpose has dimension 2, and that any vector over here is a sum, a unique sum of some vector in this column space and some vector in this null space. Now, we know that that's not all that important for what we're talking about right now, but as we get more into it, it becomes important. What we want to see now is that your B vector, which is this, which is a vector with 5 components, can't be expected to be in your column space. It might be, but if this is real world data, it's next to certain that it isn't. If it is, then we're going to be able to get a model that accurately predicts all these y values. If you plug the t into that model, you'll always get the correct y value. We don't expect that. We expect that the B vector is not in the column space, that the B vector has a component in the column space and a component in the null space. Okay, now, here we have some vectors, some x vectors. Okay, remember each x vector is like an A, B, C. A possible value of A, B, and C. It's a possible triple of values A, B, and C. So, coincidentally, I have 3 of them, but that doesn't have anything to do with the fact that this is R3. I could have, I could have another one up here. We go someplace down here. Okay, so each of these points represents a vector in R3. So this vector would map here. Now, each vector has to map onto the column space, and I've represented the column space just by a single axis, so I'll just represent where that goes by a single point on that axis, although it's actually a point in a three-dimensional subspace of R5. Okay? Now this is another point. This maps to another point. This maps to another one. This maps to another one. Now each of these points defines a vector. So for example, this point here would define a vector from the origin of the C subspace, whatever that happens to be, out to here. Now what's the distance of that vector from the B vector? Well, distance of that vector from the B vector is the length of this vector. Okay? The distance of this vector, the distance of this vector, the distance of this vector, we just do a vector from each of these points to the tip of the B vector, and we have the distance of that vector, the vector represented by that point from the B vector. Now, which point along here on this axis defines the vector that's closest to B? In other words, what point on this line is closest to the tip of the B vector? Well, that would be the point where you project at a right angle down on to the column space. And this projection line is parallel to the null space because the column space and the null space are orthogonal. So here's this is the transformed vector AX for the vector that we're trying to find over here, the X vector, that gives us our values of A, B, and C. So this vector is the image of a vector over here, say this one. So here is our X. Hard to write here. For the best, I just about can't write here. Let's try to fit. The X equals the ABC that we put in here that gives us the best fit to this data. Now what can we say about that vector? We can say that the vector along this projection line has to be parallel to the null space, so it has to be a vector in the null space. Okay, the vector defined by this projection line. And we could call that the vector okay, the vector from here to here would be AX minus B. AX minus B then has to be a vector in the null space of A transpose. Now you say, well, the vector's over here and the null space is over here. That doesn't matter. This vector, only the direction of the vector determines whether it's in the null space or not. It's parallel to the line that I've used to represent the null space, so it's in the null space. Now that's a finer point you can think about or we can discuss. But accept that for the moment. So AX minus B is in the null space. So this is a projection of the B vector onto the column space parallel to the null space. What does this mean? This means that A transpose multiplied by AX minus B equals 0. This is an equation that just represents a system of equations that we can easily solve for X. We know B, we know the matrix A, so certainly we know the matrix A transpose, This is a matrix equation that can be expressed as a system of linear equations that can be solved for x, that gives us the A, B, and C. It gives us our best possible model for our data.